Hey folks, here we are getting ready to start the second half of the course, and section 6.1 is titled The Indefinite Integral. The objectives we're going to focus on in section 6.1 are Objective 1, verify an antiderivative. 2, evaluate an indefinite integral using the power rule. 3, evaluate an indefinite integral using the sum and difference rule. 4, evaluate an indefinite integral of a polynomial function. 5, recover a function from its rate function. And 6, recover a profit function given its marginal profit function. So here's the deal. So far what we've seen is how to compute derivatives. And when we compute a derivative, it would give us a rate function. Well, now we begin the study of calculus where we work everything in reverse. So if we're given a rate of change function and we want to come up with the original function, we're going to do a process in calculus that is called integration. In general, we're going to call, I'm going to say uppercase f, an antiderivative of lowercase f if f prime of x equals little f of x for all x in the interval. In other words, if you do the derivative of uppercase f, you get lowercase f. And this is actually going to be something we're going to remember because it's a built-in check. We're going to know if we have correct answers going forward by simply differentiating what we get as a result. We're going to call uppercase f of x plus c, where c is any real number constant. We're going to call that the general antiderivative of little f on an interval if when you differentiate uppercase f of x plus c, you get little f of x. Here's the key, the process of determining an antiderivative. Well, it's called antidifferentiation, but the key is that it's the inverse operation of differentiation. It undoes differentiation. So analogous to how addition and subtraction are inverse operations, they undo each other. Multiplication and division are inverse operations, they undo each other. Differentiation and antidifferentiation are inverse operations. They undo each other. Finally, note, the phrasing an antiderivative. When I say an antiderivative, there are going to be infinitely many general antiderivatives for any function. For example, if I tell you I'm thinking of a function whose derivative is 2x, well, the function I'm thinking of could be x squared. It could be x squared plus 4. It could be x squared plus 3. It could be x squared minus 5. It could be x squared minus 18. All of those functions I just mentioned, if you were to differentiate them, you would get a derivative of 2x. So to see how we're going to get started here, the first example I have, determine if the function big F is the general antiderivative of the little function, or the function little f. So, there's big F of x, 1/3 x cubed minus 7/2 x squared plus 9x plus c. And little f of x is x squared minus 7x plus 9. So I'm going to head off to the chalkboard now to work this out. See if you think you can come up with the answer. All right, folks, in our first example, we're being asked, is big F the general antiderivative of little f? So big F of x is 1/3 x cubed minus 7/2 x squared plus 9x plus c. Little f of x is x squared minus 7x plus 9. So when you're asked, is this the general antiderivative of this, the way you determine if it really is, you just differentiate big F of x. And if we differentiate big F of x, well, you know, the 3 comes out front. 1/3 times 3 is 1. Subtract 1 from the exponent. So that gives us x squared. When we differentiate this term, 2 comes out front. Subtract 1 from the exponent. When we differentiate 9x, we get 9. And we know the derivative of a constant is 0. So the derivative of big F of x is x squared minus 7x plus 9, which is exactly little f of x. This is little f of x. So to answer the question, is big F the general antiderivative of little f? Well, the answer is yes. So to make sure you understand how to do this, at this time I'm going to ask you to go in the homework for section 6.1, do number 9. So go do number 9, pause the video, and after you do number 9, restart the video, and I'll be here at the board working out the solution to number 9. All right, here in number 9, we're given big F of x is x to the 8th plus c, and we are asked, is little f of x the general antiderivative of big F of x? So this is our big F of x. Little f of x is x to the 7th. And so the way you determine if x to the 7th is the general antiderivative of x to the 8th plus c, you just differentiate this. So let's compute the derivative for big F. So we have big F prime of x equals, all right, do the derivative here. So the 8 comes out front. We subtract 1 from the exponent. The derivative of a constant is 0. So the derivative of big F is 8x to the 7th. Is that the same thing as little f? No, it's not the same. Because it's not the same, our answer here is no. Little f of x is not the general antiderivative of big F of x. Because when we differentiated big F of x, we did not get little f of x. This is an important skill that we are learning right now, because going forward, it's going to be how we can always check our answers, how we will always be able to know if we have a correct antiderivative. But with that said, let's head back to the slides and see what's next here in section 6.1. All right, after doing that example, and hopefully you worked through number 9 and got the correct answer, it's time to introduce some notation. So first off is we're going to use this funny looking symbol. It looks like an elongated S. It's called the indefinite integral of f. And we use that to represent the general antiderivative. You know, more importantly, that symbol, which I'm going to here in a minute say it's called the integral sign. We're going to use that symbol to communicate the operation. It communicates get an antiderivative for little f of x. And then the dx tells us, you know, we're doing it with respect to x. So in general, if f prime of x, big F prime of x equals little f of x for all x, then the integral of f of x dx equals big F of x plus c. And that whole thing, that whole package is called the indefinite integral of little f of s. In the notation, well, that symbol, the elongated s, is called the integral sign. Little f of x is technically called the integrand, and c is any real number constant. So here's how I'd like you to interpret the integral sign. It's telling you get an antiderivative or integrate. The integrand, which is little f of x, with respect to x. And you're going to know if you have the correct answer by differentiating big F of x plus c. So whatever you come up with, differentiate it. And it better be the integrand. As I just said, dx tells us the variable of integration. And if we can come up with an indefinite integral of a function, so an indefinite integral, if we can integrate the integrand, we say the function is integrable. All right, now just like we had some rules for computing derivatives, we have rules for computing antiderivatives, or we have rules for what is called integration. So here's the power rule for integration. You know, for any number, any real number n, as long as n does not equal 1, that should say as long as n does not equal -1. I'll make a call out there. So as long as n does not equal -1. The indefinite integral of x to the n is, well, there's the rule. So the integral of x to the n dx equals 1 over n plus 1 x to the n plus 1 plus c. And that rule's true as long as n does not equal -1. And you can see why n can't be -1. I mean, if n were -1, 1 over n plus 1 would end up being 1 over 0, and we know you can't divide by 0. So the process that I go through when I use the power rule, and I'll draw it out in the next example, is, you know, when I'm integrating using the power rule, I get my new exponent first. And I get my new exponent by adding 1. And then the little number that goes out front, the 1 over n plus 1, that little number is going to be the reciprocal of my new exponent. So in this example, we're going to do the following indefinite integrals. And I have 3 of them here. In A, we're going to integrate x to the 8th dx. B, we're going to integrate the 5th root of x cubed dx. And in part C, we're going to integrate 1 over x to the 4th dx. So make sure you write these down. You know, I'm going to head off to the chalkboard to do each one of these. All right, here in this first example, we're going to practice using our first rule, which is called the power rule for integration. So in part A, we're asked to integrate x to the 8th dx. Now again, keep in mind what this is really telling us. I interpret the integral sign as saying, hey, the integral sign means get an antiderivative for x to the 8th. Remember, x to the 8th, this would be called the integrand. And do it with respect to the variable x. So here's how I use the power rule. You know, remember integration, it's the inverse operation of differentiation. So with the power rule, because it's the inverse operation, I start off by saying, well, the first thing I have to do is add 1 to the exponent. So when I add 1 to the exponent, I leave a little space here, I get x to the 9th. Now in the formula for the power rule, you know, you see that 1 over n plus 1 that's in the formula. Here's how I do it. I get my new exponent first, which is 9. Then the little multiplier that goes out front is the reciprocal of the new exponent. So the reciprocal of 9 is 1/9. And then I have to remember to toss on the plus c. So here's how you know if you really have done the integration problem correctly. It's how we started the section. You know this really is the correct antiderivative by differentiating. Differentiate this, and you better get the integrand. And a quick check. The derivative of 1/9 x to the 9th plus c. If I were to differentiate this, the 9 would come out front. I'd subtract 1 from the exponent. 1/9 times 9 is 1. Subtract 1 gives me an exponent of 8. That's x to the 8th. Moving on to part B, before I can even think about doing any calculus, before I can think about using the power rule, I have to rewrite the integrand. Right now we're saying let's integrate the 5th root of x cubed dx. So I have to rewrite that. Now remember, the 5th root of x cubed. 5th root can be rewritten as an exponent of 1/5. So 5th root of x cubed can be rewritten as x to the 3/5. So now when I integrate x to the 3/5 with respect to x, just using the power rule. So Power rule says add 1 to the exponent. That gives me my new exponent. So 3/5 plus 1. Well, that's 3/5 plus 5/5. That's 8/5. And then the little multiplier that goes in here is the reciprocal of the new exponent. So the reciprocal of 8/5 is 5/8. And I have to remember to put on the plus c. And again, differentiate this. You better get that back, and you will. So in C, before I can think about doing any calculus, I need to rewrite the integrand. You know, I'm integrating a 1 over x to the 4th dx. So I can use a rule of exponents and rewrite 1 over x to the 4th as x to the negative 4th. And now I simply use the power rule. So the power rule says add 1 to the exponent, so that gives me a negative 3. The little multiplier that goes in front is the reciprocal of the new exponent. Well, negative 3, the reciprocal of negative 3 is negative 1/3. I tack on my plus c. And I could rewrite this as negative 1 over 3x cubed if I didn't want to see a negative exponent in my final answer. So there's 3 examples of using the power rule. And we had to use some algebra to get us started in parts B and C. So to practice using the power rule, I would like you to now, in section 6.1, I would like you to do number 21 and number 23. So go ahead and pause the video, do numbers 21 and 23. After you've done numbers 21 and 23, restart the video, and I'll be here at the board to work out the solution to make sure you're correct. All right, in number 21, you were asked to integrate 1 over t cubed dt. So first thing you needed to do was rewrite the integrand, 1 over t cubed, using an old rule of exponents, so you could then do the calculus. In other words, you needed to rewrite this 1 over t cubed as t to the negative 3rd. Now you can use the power rule. Now we're ready to do the calculus. So the power rule, add 1 to the exponent. That gives us a negative 2. The little multiplier in front is the reciprocal of the new exponent. So the reciprocal of negative 2 is negative 1/2. And remember to tack on the plus c. And again, if I didn't want to see a negative exponent here, I could rewrite this as negative 1 over 2t squared plus c. So that's it for number 21. Number 23, you were asked to integrate the 4th root of x to the 5th. So just like we saw in the example, we have to start off using algebra and rewrite the 4th root of x to the 5th as x to the 5/4. So now when we integrate, we're just using the power rule, add 1 to the exponent, so 5/4 plus 1, that's 5/4 plus 4/4, so that's 9/4. The little multiplier in front's the reciprocal of the new exponent. The reciprocal of 9/4 is 4/9. Tack on a plus c. One more time. You know you have the correct answer here by differentiating what you think the antiderivative is. And when you differentiate this, you better get the integrand. Same thing here. You know you're correct. Differentiate it. You better get the integrand. So hopefully you were able to get 21 and 23. But let's head on back to the slides and see what new rules are heading our way. All right, hopefully you were following that example and that you were able to do number 21 and number 23 without a problem. So moving on, we're going to get some more rules here in Objective 3. The next rule is called the constant rule for integration. This is pretty straightforward. If k is any real number, then when you integrate k dx, well, you get the antiderivative to be kx plus c. This rule is really nothing more than a special case of the power rule. So if you go back to the power rule, you look at the power rule, and you let n be 0, it's just a special case of that. But it's pretty friendly. For example, if you're going to integrate a 3 dx, well, the antiderivative of 3 dx is simply 3x plus c. The next rule is the sum and difference rule for integration. It's going to look very similar to the sum and difference rule for differentiation. So if you have two integrable functions, f and g, when you're integrating f of x plus or minus g of x dx, and you could have more than two terms in there, you can split the integration up and do it term by term. So you can rewrite that as the integral of f of x dx plus or minus the integral of g of x dx. So to see how to do integrals where these rules may take place, I have an example here, two parts. Part A, we're going to integrate x to the 4th plus 1 dx. And in part B, we're going to integrate the square root of x plus 5 dx. So I'm going to head off to the chalkboard now and work through these examples. So write them down, and here we go. All right, now we've added a couple of new rules for computing integrals, for integrating. The constant rule and the sum and difference rule. So here for this example, part A, you're asked to integrate x to the 4th plus 1 dx. I'll put in all the steps showing how to use the sum rule. But it's very similar to what we did when we computed derivatives using the sum rule or the sum difference rule. You just do it term by term. So to write down what that means, doing it term by term, you could take this and rewrite it as x to the 4th dx plus integrating a 1 dx. Then use the power rule on x to the 4th. So add 1 to the exponent, and then the little number out front's the reciprocal of the new exponent, plus, now the antiderivative of 1 dx, that's the constant rule. The constant in question here is the number 1. So in the constant rule, that's the k value. So the antiderivative of 1 is just x, and tack on a plus c. Now remember, you know that if this is the correct antiderivative, differentiate this. And when you differentiate this, you would get x to the 4th plus 1, which is the integrand we started with. So we know this is correct. Now in part B of the example, we do have to start off with a little algebra. We have to rewrite the square root of x as x to the 1/2. And, one more time, I'll write down the steps showing the usage of the sum rule. But really it's just doing term by term integration. But let me write that step down. The antiderivative of x to the 1/2 dx plus the antiderivative of x dx plus the antiderivative of 5 dx. Okay, so now when we integrate x to the 1/2, using the power rule, we add 1 to the exponent, so 1/2 plus 1, that's 1/2 plus 2/2, so that gives us a 3/2. The little number in front is the reciprocal of the new exponent. Integrate x, keep in mind this is x to the 1st power, so when we use the power rule, we're going to get x squared. The little number in front's the reciprocal of the new exponent. And then when we integrate 5, well, that's just the constant rule. So the antiderivative of 5 is just 5x. Now, if you were wondering, when I came up with an antiderivative here, why didn't I put a plus c? Here, a plus c, and then for this one, a plus c. Well, if I were to do that, I would have 3 c's in there. If I add all those c's together, I would get 3c, but c is just a constant. So 3 times a constant is just a constant. So that's why I only need to add 1 c at the very end. One more time. You know this is correct. You know you have the correct antiderivative by differentiating it. If you differentiate this, you will get the original integrand. And that's your built-in check. So that's it for this example. So hopefully these make sense. Let's head back to the slides and see what we have coming up next. All right, I hope that example made sense. Our next rule is called the constant multiple rule for integration, and it looks very similar to the constant multiple rule for differentiation, which these rules should be somewhat similar, since differentiation and integration are inverse operations. So this rule says if you have any real number k and any integrable function f, when you're integrating k times f of x dx, and k is just a real number in there, you could rip that real number out front of the integral sign. In other words, you can rewrite the integral k times f of x dx. You can rewrite that as k times the integral f of x dx. So, of course, we have an example to look at. So we're going to do the following integrals. In part A, we're going to integrate 3t cubed minus 4t squared plus t minus 12 dt. And in part B, we're going to integrate the quantity x squared plus 4, that quantity squared, dx. So in this example, you're going to see all rules kind of being used. We're going to be using the sum and difference rule. We're going to be using the power rule. We're going to use the constant multiple rule, and we're going to use the constant rule. So let's head off to the chalkboard and do this example. All right, the new rule we saw was called the constant multiple rule. And keep in mind the constant multiple rule basically said that when you have a constant being multiplied by a function, so when you're integrating a constant times a function, you can rip the constant out in front of the integral sign. So our first one here is going to make use of like every rule that we've seen so far. So I'm going to put in as many steps as possible. And the first thing what I would do is make use of the sum and difference rule. So that means I would be integrating a 3t cubed dt minus integrating a 4t squared dt plus integrating a t dt minus integrating a 12 dt. All right, so that's using the sum and difference rule. Now to use the constant multiple rule. 3 is a constant, so I can rip the 3 out front of the integral sign. So let me do that. Four is a constant, so I can rip 4 out front of this integral sign. So let me do that. Don't need to rip out the 1. And that's just the old constant rule. So I'm just going to write it down. So now here we go. We're going to go through term by term, getting an antiderivative. So for the first one, I bring the constant down. And I know I'm going to be using the power rule on the antiderivative of t cubed. So when I integrate this t cubed using the power rule, I know there's always going to be a little multiplier that goes in front. So I just kind of generically put down a set of parentheses that I know I'm going to have to insert a multiplier in there. So let's see, the antiderivative of t cubed. So the power rule, add 1 to the exponent. So that gives me a 4. The little multiplier that I'm putting in here, remember it's the reciprocal of that new exponent. So it's a 1/4. Moving on. I'm using the power rule to integrate a t squared dt. So I smack down an empty set of parentheses, use the power rule. Power rule says add 1 to the exponent. The little multiplier I'm going to put in here is the reciprocal of the new exponent. That's our power rule. So that gives me a 1/3 plus, well, the antiderivative of t. So I add 1, power rule, add 1 to the exponent. And then the little multiplier that goes in front is the reciprocal of this new exponent. Then our constant rule. Well, the antiderivative of 12 with respect to t is a 12t. And then I tack on the plus c. You know what? Let's just clean this up a little bit. Just a little. Why don't we say 3 times 1/4? We know that's a 3/4. And 4 times 1/3, we know that's a 4/3. So it didn't take a whole lot to clean it up. And again, I'm stressing this a lot. I know this is the correct antiderivative for the original problem by simply differentiating this. And when I differentiate this, I better get the integrand. All right, let's look at part B here. We're asked to integrate x squared plus 4, that quantity squared. So the only thing we can do now is we have to start off by doing some algebra. We have to take x squared plus 4 and we have to square that. So we have to FOIL it out. And when we FOIL it out, we get x to the 4th plus 8x squared plus 16. Then, I'll put in every step. That's using the sum rule. I can split this into term by term, integrating the following. So the following 3 integrals. And you know what? There's a constant right here. So let me put in 1 extra step. Just having fun putting in as many steps as possible. I could take the constant and rip it out front of that integral. Now I go through and I do term by term integration. The antiderivative of x to the 4th using the power rule. I would add 1 to the exponent. The little multiplier in front is the reciprocal of the new exponent. Plus, don't forget that 8. Antiderivative of x squared, power rule. I'd add 1 to the exponent, which gives me a 3. The little multiplier in here is the reciprocal of the new exponent, so that's a 1/3. And then the constant rule, the antiderivative of 16 is 16x. And, we could go ahead and say it's 1/5 x to the 5th plus 8/3. We could multiply that together to get 8/3. X cubed plus 16x plus c. So there's 2 examples, kind of using all the rules. So to make sure you're feeling comfortable about using all these rules, I'm going to ask you now in section 6.1 to do numbers 33 and number 39. So go ahead, pause the video, do numbers 33 and 39. Once you've completed them, restart the video and I'll be at the board working out the solution to those 2 exercises. All right, folks, hey, at number 33, you were asked to integrate 3t squared plus 2t plus 10 dt. So, I'm going to go ahead and put in every step. You could start off by using the sum rule and rewrite this as the following. Then on this first integral, you can use the constant multiple rule. You can always rip a constant. You can rip a constant out front of the integral sign. And I could use the constant rule here, constant multiple rule here, to rip a 2 out front. And now we just kind of do it. It's a Nike problem, so we go ahead and use the power rule. 3, leave a little space, antiderivative of t squared. I add 1 to the exponent, gives me a 3. The little multiplier in here is the reciprocal of that new exponent. It's the power rule. Plus 2, antiderivative of t to the first, so the new exponent would be 2. The little multiplier in here is the reciprocal of that new exponent, so it's 1/2. And then the antiderivative of 10 is 10t. And then I'm going to clean it up a little because 3 times 1/3, that's kind of neat. That's just 1. So we get a t cubed. 2 times 1/2 is 1. So we have t squared. And you can quickly check that this is the correct answer by differentiating it. And if you differentiate this, the derivative is 3t squared plus 2t plus 10, which is the integrand. Now number 39, just a little bit more involved. And then at number 39, we have to start off by using a rule of algebra, a rule of exponents, to rewrite. So in other words, 1 over x squared, we rewrite that as x to the -2nd. The 3 over x cubed, we rewrite that as 3x to the -3rd. Then if I use the sum difference rule, I can split it into 2 integrals. So let me write that down. And then we have the constant multiple rule. It can be used here. I can take this 3, rip it out front of the integral sign. All right, so here we go. Be careful. When you're integrating using the power rule, remember you're adding 1 to the exponent. So my new exponent here, I add 1. So -2 plus 1 is -1. And then my little multiplier out front is the reciprocal of the new exponent. Well, the reciprocal of -1, that's right, it's -1. Minus, don't forget the constant, 3. So power rule on integrating x to the -3rd. So I add 1 to the exponent. So -3 plus 1, -2. And the little multiplier I put in here as a result of the power rule is the reciprocal of the new exponent. Well, the reciprocal of -2, it's -1/2. Tack on the plus c. And, we could just rewrite this as -x to the -1st. And then, see, if I take the 3 times the -1/2, that gives me a -3/2. So minus a negative, that's a plus 3/2 x to the -2nd. And then if you wanted to get rid of the negative exponents, you would have -1 over x plus 3 over 2x squared plus c. And that's it for number 39. So hopefully when you did 33 and 39, you were able to get the correct answers. So it's time to head back to the slides and see what all this stuff we're doing right now has to do with recovering a function from a rate function. All right, after doing that last example, hopefully you were able to crank through numbers 33 and 39 as I asked you to do. Our next task is to kind of start to look at why we are learning this undoing behavior called integration. So first off, any function that gives an instantaneous rate of change. We know that is a derivative, but in general, any function that gives an instantaneous rate of change is called a rate function. And yes, a rate function may be considered a derivative since the derivative gives us an instantaneous rate of change. Now, after we integrate a rate function, we may be given a condition for the original function, and that will help us solve for the constant of integration c. Now, generally for any rate function, the units are given in dependent units per independent units, and the function recovered is just measured with dependent units. So think about what that means. We've done a lot of work in the first half of the course of coming up with the derivative, evaluating it, and interpreting. And remember, in the interpretation, you had to have appropriate units like dollars per year, fish per year. Those are dependent units per independent units. Well, when we undo it, when we integrate the rate function, we're going to end up with just units that are dependent units, like dollars or fish, for example. So to kind of see how this works, let's check out this example. This example, I'm going to be heading off to the board to work this example. So if you need to pause the video to write all this down, take this opportunity now to do that, because I'm heading off to the board, to do the problem. All right, hopefully you wrote this example down in your notes, because I'm not going to write all the words on the board. I just pulled out the function that we're talking about. The rate function that we were given was f of x equals negative 0.34x plus 3.82. That is a rate function. I know it's a rate function because it says f is the rate of change of the employment rate in percent per year. So it said f is the rate of change of the employment rate in percent per year. Percent per year. That's reminding me of the interpretations we did in the first half of the course. And then I also wrote down x represented the number of years since 2000. So in this example, it said knowing the unemployment rate was 5% in 2011. So knowing, let me write that down. Knowing the unemployment rate in 2011 was 5%, we're asked to find the function that models the unemployment rate. So we have the rate of change function for the unemployment rate. We're asked to come up with the function that models the employment rate. So that means we have to undo this. This is a derivative. It's a rate of change function. This is a derivative for some function that models the unemployment rate. So to undo that, we integrate. So let me write that down. To come up with the function, which I'm calling big F of x, that models the unemployment rate, we have to integrate the rate of change function. So we have to integrate little f of x. We have to integrate negative 0.34x plus 3.82. Well, I'm not going to put down every step now. I'm just going to kind of verbalize them. There's the sum rule in here. So we're going to integrate term by term. Here's the constant multiple rule. So when I integrate negative 0.34x, I have the constant negative 0.34. Let me leave a little space, because when I integrate the x, I'm using the power rule, so I'm adding 1 to the exponent to get a 2. And then I put the reciprocal of the new exponent in here, which is 1/2. And then the antiderivative of 3.82 is 3.82x plus c. So here's where we're at. We know this big F, the function that models the unemployment rate, is equal to, let's see, negative 0.34 times 1/2, that's negative 0.17. We know it's this function right here. In fact, do a quick check. Differentiate this, and you're going to get the rate of change function. But what we don't know for the function that just models the unemployment rate, we don't know what this constant is. We don't know what c is. That's where this information comes in. We know the unemployment rate in 2011 was 5%. Well, first off, the year 2011, since x is the number of years since 2000, 2011 would be 11 years after 2000. X is 11. So this tells me x is 11. We know the unemployment rate in 2011 was 5%. So that means when I toss 5% in, when I toss 11 in for my x, because x is 11, the number of years since 2000, I know when 11 comes in here for the x's, what has to come out is 5. It's almost as if that's a y coordinate. It's almost as if what we know right now, we know that when x is 11, the y value is 5. So it's this point, 11, 5, would be on the graph of this function. That helps me find c. I mean, think about what this means. When 11 comes in for the x, so let me do that. When 11 comes in for the x, I'm just putting 11 in for the x's. What has to result from the 11 going in for the x's, all of this stuff here has to kick out a result of 5. 5%. It has to kick out 5. So when 11 goes in for the x's, I have to get a result of 5. Well, when I look at this, let's see what I got. If I take negative 0.17, multiply that by 11 squared, plus 3.82 times 11, that ends up being 21.45. So I have 21.45 plus c equals 5. Well, how do I determine c? Just subtract 21.45 from both sides, and we get c is negative 16.45. So now that we know c, I can take this value for c, I can toss it in here, and that tells me f of x equals negative 0.17x squared plus 3.82x and c is negative 16.45. This is the function that models the unemployment rate. And you will know you've done everything correct by, you can check your work. First, if you differentiate this, do you get this rate of change function? The answer is yes. If this models the unemployment rate for the year 2011, since X is the number of years since 2000, you should be able to put 11 in for the X's, and the result, what should come out is 5. 5%. That 5 should come out. So you should be able to put 11 in for the X's, and 5 would come out. So that's like a built-in check. So this is the beginnings of like examples of why we're learning this undoing process, like to recover a rate function. We're going to see through the rest of the course how powerful integration is in applications and what all it can do for us in applications. But in this section I want to do one more example where we'll actually deal with a marginal business function. I believe the example I want to look at is a marginal profit function and how we can recover the actual profit function if we know the marginal profit function. So let's head back to the slides to see what this next example is, and then we'll be coming back to the chalkboard to work through the example. All right, that last example, hopefully we saw we had to pay particular attention to the units that were involved, and we saw how to check. And we were able to come up with the original function that modeled the unemployment rate in Billings, Montana, given the rate of change function. So we're going to conclude this section with an example where if we know a marginal profit function, how we can recover the profit function. So, I'm going to be heading off to the board to do this example on the board. So again, if you need to pause the video to write down this example, in your notes, take this opportunity to do it. I will point out before I head to the board, it looks like here X is the number of treat bags in thousands, and marginal profit, MP, is in hundreds of dollars. So that tells me when I see knowing that the company makes $10,000 in profit when 6,000 treat bags are sold, well, that's 6,000, that's the number of treat bags sold. So since the number of treat bags is in thousands, I think that 6,000, that would correspond to an X value of 6. The $10,000 that profit is made, well, since marginal profit is in hundreds of dollars per bag, that 10,000 would end up being 100, because 100 is 10,000. But let's head off to the board to do this one, and you'll hopefully see what I'm talking about. All right, folks, here in this example, we were given a marginal profit function. The marginal profit function was negative 2x squared plus 45, and we were asked to recover the profit function. And I wrote up here, X represented the number of treat bags in thousands, and MP, the marginal profit, that was in hundreds of dollars per bag. So to get started, to recover the profit function, remember P of X is profit function. To recover the profit function, you have to integrate marginal profit. Integrating a derivative, integrating a rate function, they undo each other. That's how we recover the profit function. So here we have to integrate negative 2x squared plus 45. Let's see, the antiderivative of negative 2x squared. Well, that should be a negative 2/3 x cubed. The antiderivative of 45 is 45x. And remember the plus c. So right now we have the profit function for these treat bags to be a negative 2/3 x cubed plus 45x plus c. Now we need to determine the c. We need to get that constant. And here's how we're going to do it. We know this company makes $10,000 in profit when 6,000 treat bags are sold. But we have to be kind of careful here because of units that are being used. First, if 6,000 treat bags are sold, so we know 6,000 treat bags are sold. Well, X represents the number of treat bags in thousands. So that means 6,000 treat bags sold. That tells me X has a value of 6. X is in thousands. 6,000. MP is in hundreds of dollars per bag. So if I know the profit is $10,000, so likewise, what are the units here? What are the units? Well, the units are hundreds. That matches up with 100 because $100, think about it, $100 is 10,000. So X is 6, profit is 100. 6, 100. I mean, that's like a point that would be on the graph of the profit function. X is 6, the profit is 100. That point, 6, 100, has to be on the graph of the profit function. So we put 6 in for the X. And we know when 6 comes in for the X, 6 comes into the profit function for the X, what has to come out profit-wise is 100. So this has to kick out 100. Now let's see, if you take negative 2/3 times 6 cubed plus 45 times 6, I believe that's going to give you, a nice number, 126. So you have 126 plus C equals 100. So to determine C, subtract 126 from both sides. You get C as negative 26. Once you know what the constant is, you toss it back in here, and we conclude that the profit function is negative 2/3 x cubed plus 45x minus 26. We have recovered the profit function. And do a quick check. Put 6 in for the x. That would be 6 in for the x would be representing 6,000 bags of treats. Put 6 in for the x to make sure 100 comes out. And that profit, that 100 would be in hundreds of dollars. So 100 is $10,000 in profit. So there are a couple of examples at the very end of this section on how we recover functions from rate functions. This concludes the video for section 6.1. So now you can head off to the section 6.1 exercises and do the exercises so you get these basic skills of integration under control. Thanks for watching.